Welcome. Today I am going to discuss on the topic that is Orgel diagrams. Now, what is the Orgel diagrams? This Orgel diagrams, uh, this the scientist called that Leslie Orgels. He give the names. This Orgel means after he discovered this Orgel diagrams. So after that, this diagrams name came Orgel after his name. So the scientist who after whom its name come is Leslie Orgel. Okay, and this Orgel diagrams, what is it? This is the one type of correlations diagrams. One type of correlations diagrams, which which shows the relative energies, relative energies of electronic terms in transitions of metal complexes. So this diagram is one type of correlation diagrams where we see that the relative energies of electronic terms. Okay, these terms we have discussed in the previous class, terms and term symbols. So here this through this other diagrams we will see that how that relative energies of that electronic terms in the transitions of metal complexes. Okay, and some points we have to note while discussing on these Orgel diagrams. So some important points. Okay, or you can say that this Orgel diagrams only apply in this case, or you can say that limitations of this Orgel diagrams. Okay, so only these conditions, these Orgel diagrams will apply, or you can say that conditions of Orgel diagrams. Okay, so past conditions is that it is only allowed in spin allowed transitions. Very important points. First point is it is allowed only spin allowed transitions. Okay, so like if it is that let's say 1 2 3 4 and 5. So here that already this is this here. Okay, so now I want to do one electron transitions. So if I do the transitions, then here that spin is allowed. Okay, so here if I transfer here, then we will get this one, and this is already like this, and this. So this is the spin allowed. Okay, now so this type of transitions are possible. Spin allowed transitions. But if it is like this, suppose let's say it is like this, and we want to do the transitions now. this is the one electron I want to do the transitions. Then what here this is in this form. Now I am doing the transitions here, so this will be change its spin, because I will do the transitions. So if this is in this form, now after going that will change to this, so this spin should not be changed. Okay, so if spin is changing, then this will be not transitions. Okay, so the spin should not be changed, this is not allowed. But here this is spin allowed. So first condition is spin should not be changed. Okay, that is spin should not change. This is the first conditions. And second conditions is, this is very important points. Second condition is it is allowed only for high spin complexes, that is HS. So only high spin complexes allowed, both for octahedrals and tetrahedrals. So we will go for only for that high spins. So low spins is there, then it is not allowed. So only for high spins we will do that Orgel diagrams. Okay, so first point is that spin should be allowed. Second point is that should be that high spin complexes. Okay, so no low spin complexes. Okay, so no low spin complex are allowed. Okay, this is very important points. So first point and second points. And third points, you have to note that if two transitions of same spectroscopic terms are never cross each other. What I mean that, let's say the two terms, let's say any terms, like let's say if it is we are doing that electronic transitions here, this is let's say a ligand field strengths, and let's say here that energy, and whenever we are doing that transitions, then let's say one transition is let's say this is T2G, and let's say this is EG, and if that another transitions, this is EG, or let's say this is T1G. So if another T1 is here, let's say another T1G, or I can do it. This will ligand field distance, and let's say that another will be always that will be not cross, so it will comes that are like this, so they will repel. Okay, so they never cross each others and repels with each other. if it is, let's say it is also T1G and it is also T1G, then they never cross each other, they repel each other. This is energy. Okay, so this is the one points you have to remember. And next point is uh, when the lines of two spectroscopic terms of different symmetries approach each other, they may cross each other. Okay, this actually that exact point I'm wrong. So when the lines of two spectroscopic terms of same symmetries are approaching each other, they always repulse and never cross each other. Okay, so these are the 2 points. So whenever that symmetry lines of two spectroscopic terms of different symmetries, or if in this case same symmetries, then they always repulse each other. This is the same symmetries. Okay, and if they have that, they are approaching the two lines and they have that different symmetries. Let's say one is T1G, let's say one is T1G, another is A2G, then they may be cross each others. Okay, this is the cross points. Okay, so this point you have to remember that if that lines of two spectrotrons of different symmetries, then they always they may, okay, if they are coming in contact, then they may cross each others. But if they are same symmetries, then they never cross each others, they always repulse. Okay, if they are same symmetries, okay, spectroscopic terms of same symmetries, they always repulse each others. These are the 4 points you have to note while doing the Orgel diagrams. Let me see any other points is left. These are the 4 points for Orgel diagrams. Now, so the Orgel diagrams, so we are doing that Orgel diagrams for that transitions metal complexes. Transitions metal complexes. Okay, so this transitions metal complexes, sorry, so this transitions metal complexes we are doing for transition metal Orgel diagrams for transition metal complexes. So these transitions metal complexes, they will used either D1, D2 to up to D10. So any orbitals they will use. Let's say D1, D1, D2, D3, D4, D5, D6, D7, D8, D9 and D10. So this transition metal complexes, they use the d orbitals. Okay, and the d orbitals from d1 to d2, d10. Okay, so now this Orgel diagrams, so we will divide this uh, Orgel diagrams in this in 3 parts by considering this they are using this d orbitals. Okay, so we will divide this Orgel diagrams. So three types of three ways Orgel diagrams can be drawn. So one types, second types, and third types. Okay. So first type Orgel diagrams are if they are using that D1 and D9 and D4 and D6. Okay. These are the one types of Orgel diagrams. So if the transition metal complexes, if they are using D1, D9, D4 and D6, then their Orgel diagrams will be in one same types. Means here we will draw that Orgel diagrams. Okay. And if they are using that d orbitals, that is, let's say D2 and D3 and D7 and D8, so they will do that one type of Orgel diagrams. Okay. And left is D5 and D10, and if D5 and D10, they have that some other Orgel diagrams. Okay. Now we'll discuss this. So this D5 and D10s here, that here will be the spin forbidance. So spin forbidance will occur. So we know that if spin is not allowed, then there will be no Orgel diagrams. Means there will be no peak will be observed. Means this will be the colorless, because you see that D5, if I draw here, then 1, 2, 3. So 1, 1, 2, 3, 4, 5. So if I do the transitions, then if I do this transition, then it will be forbidden. Means this one is going to change. Let's say this is there. So if I do the transition from here to here, this I have to do. So this spin is changing. So this is spin forbidden. So you know that Orgel diagrams, so you can't do the Orgel diagrams for spin forbidden transitions. So D5, similarly with D10. D10. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So if you want to the transitions here also, there will be no transitions is possible, because all are fully filled and there is no holes or no any electrons, so we should not there will be no any transitions is possible. So here D5 and D10, so there is no transitions are possible. So here we can't draw that Orgel diagrams. So we can't draw Orgel diagrams, and these are no peak will be observed in Orgel diagrams. No peak observed in Orgel diagrams. So these are colorless. Okay. So we will not speak of for whenever you are talking about Orgel diagrams, we will not speak about of D5 and D10. If ask D5 D10, then we will say that no Orgel diagrams drawn for this D5 and D10s, and there. So if no Orgel diagrams, and here that no peak is observed, and these are the colorless compounds. Okay, for D5 and D10. So now we will discuss about of the D1, D9, D4, D6, and D2, D3, D7, D8. So this is the one types, and this is the second types. Okay, this is the third types. Here we can draw here. So this is one types. So this 1 and 2 types we will discuss. Okay, and for this one types, here what we will see here is that whenever we are discussing about type 1 and this type 2, so here what you see that only one electrons or one hole is transitions is possible for one types, and two types more than uh, two more than two transitions are possible. Mainly two transitions, that we can say that more than one transitions are possible for this type 2. Okay, so now we will discuss this is type 1. These are the type 1 and these are the type 2. Okay, so this type 1, in this case only one electrons or hole, transitions possible. Okay, and for this case more than one electrons or one hole, transitions possible. Okay, so for D1 and D9 the Orgel diagrams are very simple, because we will transfer or we will do the transitions either one electrons or one hole. Okay, so now what about of this one electron or one hole? So let's clear about of this concept. What is one hole and one electrons? Okay, so let's see if we are talking about of, so we will discuss about of type 1 and type 2. On that we will discuss about of hole and electrons. Okay, so first we will discuss on the type 1. Type 1. So in this type 1, what are the there? D1, D9, D4 and D6. Okay, so here we see that if I talk about of D1, then you see that so I'm putting that one electrons, D1, one electrons. So here that how many electrons, how many transitions are possible? So one electron is there, one transitions. Okay, if you talk about according to electrons, that is one transitions. And now according to hole, so how many hole? Hole means how many space is there. Okay, so here that space is 1 and 2. For one electron we have the 2 space here. So how many according to hole, how many transitions can possible? This 2 hole is there, so 2 transitions possible. Similarly, if I say about of D9, let's say fill the electrons 1 2 3, only high spins 1 2 3 4 5 6 7 8 and 9. Okay, so for this also how many holes are there? Hole is 1. So hole is 1 and electrons, so how many transitions of electrons are possible? So here you see that 1 2 3, so anyone I can do the transitions. From here I can send this one also possible, because this one I want to put here, this is also possible, this is like this, so here also possible, and this one also possible, and this one also possible. So according to electrons, how many transitions are possible? 3 transitions possible. And according to hole, how many transitions are possible? 1 transitions are possible. And we will always take that minimum transitions. Okay, so this is the always taken minimum transitions. Minimum transitions. So here that according to electrons 3 transitions, according to hole 1 transition. So here we will talk according to the hole transitions, not electron transitions. Okay, so we will always take that minimum transitions are always considered. Okay, so for D1, so according to hole that is 2 transitions, according to electrons 1 transition. So here we will take according to the transition, according to the electrons, but here we will take according to the hole, not according to the electrons. Here not hole, here electrons. Okay, so always take that where that minimum transitions are possible, either it may be hole or it may be the electrons. Similarly, if I talk about of D4, let's discuss about of D4. One, two, three, and four. Okay, why I am not feeling like this? I 1 2 3 4. I can't feel because always high spin complexes are allowed, low spin complexes are not allowed. So I can't do that. Or always I have to do like this. Okay, because only high spin complexes are allowed. So here for D4, how many holes are there? One hole is there. How many electrons are possible? This is also possible. This is also I can do here. From here I can say no, spin is not changing, means this is there here, so this is after transition also this should be there. Okay, that is that spin is not changed. If this is there and after transition it will come like this, the spin is changed. So if spin change, then the transition is not possible, so spin has not been changed. Okay, so here this one again I can put here also, so spin is not changed, this is also possible. From here also I can put here, there also spin not changing, here also I can put, here also spin not changing. So according to electrons, how many transitions are possible? According to electrons, total transitions are 3, but hole is only 1. Here also space is there, but if I do the transition, then I have to change the spin, and changing spin is not allowed. So here how many transitions according to hole? So according to hole, transitions are only 1 transitions are possible. So here we will talk according to the hole. According to the hole we will talk, we will not talk according to the electrons. Similarly for D6, I will always pitch high spin complexes 1, 2, 3, 4, 5 and 6. Okay, so here that how many holes are possible? So here we see that here also I can put 1 electrons here, here also possible. This one I will not change, this also possible, here also I can put. So according to hole, how many, sir? 2 transitions are possible, because this one is here like this one, here also I can put like this, here also I can put like this, the space is there. So according to hole, 2 transitions are possible, but according to that electrons, only this one I can change, this one I can do, because if I put there, then there will be repulsions will start. So this I have to change that spin, so that spin change is not allowed. So only this one I can do the transition. So according to electrons, only 1 transition is possible. So here I will talk according to that electrons, not according to the hole. Okay, so this is the concept of that hole or electrons, because always we will take that minimum transitions. So wherever the minimum transition is possible, we will consider that either it may be hole or it may be the electrons. Okay, so for this type 1 we will do that Orgel diagrams. So for this type 1, only 1 electron or 1 hole is possible. Okay, for this type 1, that is D1, D9, D4 and D6, only 1 electrons or hole transitions is possible. And for this type 2, that is D2, D8, D3 and D7, more than 1 electrons or hole transitions is possible. Okay, so now we will do that Orgel diagrams. Where? In Orgel diagrams. Okay, so before we make that Orgel diagrams, it is very important to talk about of this spectroscopic terms and this Malkin term symbols. Okay, Malkin notations, because from this d orbitals we used to go past that terms we have to make. And from terms, actually how we are making in the previous class, we have to, if that orbitals electrons is given, if any orbitals d and orbital is given, we used to make that how to make the terms. We will make the terms and term symbols, term and term symbols we used to we have to calculate the terms and term symbols, and from the term symbols we will make that Malkin notations. So it is already pre discovered that for this type of d orbitals, these types of terms are there, and for these types of terms, these types of Malki notations are there. So that no need to be calculate more and more, because that is already discovered. So you see that for d1, so how they already discover that whenever d1 orbital is there or d9 orbitals is there, then for that terms are always that will comes, the terms is d2 will comes. Okay, that is already discovered. And if that this is that orbitals, if orbitals is d1 and d9, then that is always the terms will got d2. Similarly, if that orbitals is d2 and d8, why I'm saying d1 and d9, add that is actually 10. Okay, d1 d9, similarly d2 d8, 2 plus 8, that is 10. Okay, for this type of d orbitals, any complexes it have, then the terms are always that is f and 3. Okay, and if that is d3 and that is d7, okay, 3 plus 7, that is 10. Okay, so if this is there, then that is again df, that is 4. And if it's d4 and d6, then that terms is again d, and that is again 5. So 2 3 4 5. Okay, and it is d5, then that will be that s, and that is 6. Okay, so these are that already discovered, that if d1 and d9 is there, then terms are d, and this one we can 2 3 4 5 6. Okay, so we can remember that d f f ds, we have to memorize this. So d f f ds. Okay, so this is, and d1 plus 1 plus 2 2 3 4 5 6. So it will start from 2 3 4 5 6. Okay, this you have to memorize. And this is the for ground state. And for excited state, for this excited states, for d2 and d8, here we will get that 3p, and for this d3 and d7, so we get that 4p. Okay, so this is that so this is already discovered, and this is known that if d1 and d9, then terms always d2, and d2 and d8, then f, that is 3, and this is d3 and d7, that is 4p, and d4 and d6, and that is d, and this 5, and d5, and then that is d6. And for this is the ground state for excited 3p and 4p. Okay, so this we have to memorize, or it can be easily remembered. Okay, so d1 and d2, so add to that, so that we will get the 10. Okay, now another we see that this s, okay, these terms, and how these terms are related with Malki notations. So I am doing that Malki in these terms. Let's say s, or I can do it here. Okay, terms, terms, uh, terms are s, p, d, and f. Okay, that we discuss d, f, f, ds. So these are the terms. So I'm doing that s, p, d, f. These terms we have. So these are the terms. Okay, these terms, and these are the terms. Okay, these terms, how these terms are related with Malkin notations. Okay, now I'm doing here Malkin notations. So whenever this s is there, or this s, you see that we have seen that whenever that s is there, so we have seen that when we are discussing about of terms, whenever that s is there, then that is always in the ground states, and we used to get that only one uh, one symmetry terms. So that is only one terms we used to get, so that is a1g. Okay, and this is, let's say, for octahedral case, and let's say here tetrahedral case. So that is we used to get always, or I can octahedral and here tetrahedral. If S, C, D and F. So whenever that S is there, so on that case, what we see that this is the, whenever terms is S, so we say that this is L equal to 0. So that is mainly, that is has to be the ground state. So that is one molecule notation, so we will get that is A1G. Okay, and we know that this A, we have discussed in group theory, A, T, E. Okay, this A is non-degenerates, and this T is triply degenerates, and this E is doubly degenerates. That we have discussed in, so while we are discussing in group theory, so we will discover, we see that A is non-degenerate, T is triply degenerates, and E is doubly degenerates. So S is, that is the ground state, mainly this is that ground state we are seeing that. So whenever S, then that molecule notation is A1G. Okay, and here also that tetrahedral, so no that cos is not present, so we will discuss only, we will say only A1. Okay, so this G and U will not come. Okay, and for P, that will be the T1G. Okay, and this is the T1. Okay, and for D, so we remember that D, so this is mainly for D orbitals we are discussing. So in, see that D orbitals, these things are there. So either this is two orbitals there, either it which doubly degenerate, that means T, or it is triply degenerate, that means T. So here we will get either T2G or EG. Okay, because either this is triply degenerate or doubly degenerates, and this for here, that is T2 plus A. So note that here I am not talking about, this is not d orbitals, this is not d orbitals. I am saying that this is mainly we are discussing for that for this transition metal complexes, and for this we see that that is uh, for this mainly we will get that type 1. So here only we will see that T2G and EG, and this T2G is due to this and EG is due to this. Okay, and whenever we talk about of F, then here we will get that T1G and plus T2G and plus A2G will get here. Okay, and for tetrahedral, that is T1 plus T2 plus A2. These are the molecule notations for tetrahedrals, for octahedrals and tetrahedrals. So we can easily remember that S, that is mainly ground state, so that is only one molecule notation you will get, that is A1G, and this is A1. And for p orbitals, that we will get T1G and this is T1. So one triply degenerates you will get, and for D we will get T2G and EG, and this is T2 plus EG, and for F we will get D1G, T1G, A2G, and this. So we can easily remember that. So this we can memorize by taking that d orbitals. Yes, because d orbitals we have that either doubly degenerates or triply degenerates. So that's why this value. And for F we will see that T1G will come, T2G will comes, after that A2G will comes. Okay, so these are the two important things, and these are the repeatedly used in doing Orgel diagrams. Okay, so these are the very important. Only these two terms you have to remember, T2G and EG here, and this T2G T1G plus A2G, and whenever we are talking of tetradels, this GU will not come. Okay, so these are the terms and molecular notations and orbitals. These are the terms and how these terms are related with molecular notations we have seen. Okay, so now using these concepts we will draw the Orgel diagrams. Okay, so any problem of memorizing this? Because we can easily memorize it. First will be A1G because that is S, that is mainly that ground state, so that's only one molecular notations we will get. Next for P, T1G, and for D and F, for D we can remember by doing that D orbitals, but be sure that be not that this is not D orbitals, because this is also D orbitals. Okay, so for memorizing we can insert D orbitals, there is two uh, that states will get, either it will be doubly degenerates or triplet degenerates. That's why T2G and EG, because we say that this is EG and this is T2G. Okay, so likewise you can memorize it, and this molecular notations we will remember as DFFF DS. Okay, and we can do that here for D2 and D3, that is B3P and 4P excited state is there. Okay, here no excited states are there. Okay, so these are the ground state and this is for the excited state. Okay, so now we will draw that Orgel diagrams for type 1 and type 2. So for type 1, D1, D9, D4, D6 is there, and for type 2, D2, D8, D3, D7. And we will talk here only one electron or one hole transitions is possible. Okay, that may be electrons or maybe hole, but one transitions is possible for type 1, and for type 2 more than one. Mainly that is mainly two transitions are possible. Okay, for type 2. So let's discuss about of type 1. That is D1, D9, D4 and D6. Okay, so for D1, so first we will now go with D1. Okay, so for this D1 we see that I will draw here 1, 3. Okay, so now only one electron, so I fill one electrons. Okay, so here how many electrons transition are possible? And one electron transition and two holes are there, so here we will talk according to that electrons. Okay, because two holes and one electrons, and which is less minimum, that we will talk accordingly. So one electron transition is possible, so I will talk about up here according to the electron transitions. This one I will do the transitions if I give the heat. Okay, so this transitions is possible, so here the transitions is occurred. Okay, so here I am talking about of according to electron transitions, that is one transition is possible, and according to hole, how many holes? Two holes are there, so two transitions are possible. So here I am not talk about of hole, I will talk about of electron transitions. Okay, this I will not talk. Okay, so now so one electron transitions are possible. Now what we will do that, calculate that CPS CFSE for this both the cases, and give the names that are molecular notations where it is non-degenerates. Okay, so we know that what do you mean by degenerates and non-degenerates. So if it is like this, see, if the electrons are, let's say, this way, so this and let's say this and this, so in this case we see that this is all are half filled, so this is non-degenerates. So here this is, here that non-degenerate states is present. Okay, non-degenerate states is present. Here all are in a degenerates. Okay, so and in this case, another example if I talk, So in this case, here that all are vacancy, but here that electrons are there, but here not, no electron is there. Here the non-degenerates is there. So what we do that, first calculate the CFSE for both the cases and give the names of that molecule notations where degenerate state is there, where non-degenerate, where the degenerate state is there. Just a minute. So where this is actually degenerates. This is that, here that doubly degenerates. Okay, so here the degenerate state is there. Degenerate state is there. Okay, so here the degenerate state is there, and this is triply degenerates. Okay, and this is doubly degenerates, and this is non-degenerate state. Okay, so all are there. So no degenerate is there. This is not degenerates. Okay, so what I will do, first calculate the CFSE for the both the case. So if I calculate the CFSE, then how will calculate? We have discussed it so many times that here that what you say that here it will be 0 point, because this is 1 2 3. So calculate that such that here and here it has to be equal. Okay, so here, so how, if I multiplied by 3 orbitals, so 3 orbitals if I multiplied by 4, and here 2 orbitals multiplied by 6, then both the cases I will get 6. Okay, because see that here 2 orbitals, so 2 into 6, then I will get 12. Okay, here 3 orbitals, 3 into 4, then I will get 12. So what I do that, here multiplied by 0.4, here I will multiply by 0.6, so that both the cases I will get 1. Okay, so here if I multiplied by both the cases I will get same value. So here that 0.6, then here I will get 1.2. Here if I get 3 into 4, then here also I will get 1.2. So both the cases I should get the same value, because they are actually same value, they are doing the they equally dividing. Okay, so if it is 2 orbitals, then I will multiply by 0.6. If 3 orbitals, I will multiply by 0.4. Okay, so here 1 electron is there, so for 1 electron, so 1 electrons is there, so 1 into 0.4. Okay, and this is negative because this is the low energy, and this is positive because this is in high energy. Okay, from here this is high value, so this is positive value, and from here this less, so this is the negative value, and this value is delta naught. Okay, so this value will be 1 electrons into this is minus 0.4. So CFSE will be minus 0.4 delta naught. Okay, and for this case, here we see that here that here this is 0.6, here it is minus 0.4. So CFSE will be, that is equal to 0.6 into 1 electrons. This value will be 0.6 delta naught. Okay, these are the CFSE. So now what we will do, that assign that value where the degenerate state is there. Okay, sorry, here electrons was there, so assign the value where that degenerate state is there. So here that here it is triply degenerate state is there, so I will assign this value as, what is the value of this? This is triply degenerate, so I will do that T2G. Okay, because I am talking about a D1. So for D1, what things are there? That is D2, because we have done this. For D1, that is D, and if D, therefore D, that is T2G and EGs are there. So that's why I will do here D1. So it means that this is a D2. It means that here T2G and EGs are present. So here I will assign that where that degenerate state is there, I will assign that value. So here degenerate state is there, so it is D2G. Here I will not assign because here no degenerate state is there. Okay, so I will assign here T2G, and here that not degenerate state is there, here degenerate state is there, and it is doubly degenerate, so I will assign here as G. Okay, so now that how that electron transitions are occur from this to this, so from T2G to EG. So here electron transition is I am doing from these two. I send here. So from T2G to EG I will send. Okay. So electron transitions happen from electron transitions happen from where? From T2G to EG. Okay. I did that from electron transition from T2G to EG. And and what I see that here, that is D1 is D2. So here also I will put 2 and 2. So here also I will say that 2 and 2. Okay. So this is the electronic transitions for the case of D1. Okay. So how I will draw this Orgel diagram for this. So Orgel diagrams. Yes, this is the energy, and this is that ligand, field strength, that is LFS. Okay, this is the energy. So now I want to do that Orgel diagrams for this. Okay, so here that electron transition is happening from EG to T2G. Okay, so this we will look that CPSC. One is 0.4 delta knot, another 0.6 delta knot. So what I'll do here, one is 0 minus 0.4 delta knots, another is 0.6 delta knots. Okay, 0.6 delta knots. Okay, so that electron transitions is happen from this to this. So this is that Orgel diagrams for D1. Okay, and note that here this one, this gaps and this gap and this gaps is everywhere. This is delta knots, because if you see the 0.6.0.4, if you add it 0.6, so that how will add, that is on this minus this, so 0.6 minus 0.4 delta knots, then that how will get, this is delta knot. Okay, so this value will be, we will add it 0.6 plus 0.4, that is going to be that 1. Okay, so this delta knot always has to be 1 values. Okay, so here what we see that according to that picture, we see we should get that one electronic transitions. But whatever we see that whenever you see that actually that peak, then some shoulder peak will occur, some broad peak is observed in that Orgel diagrams. The reason behind this is actually you should get that one Orgel diagrams. Okay, so okay, before that I would like to clear one point. So here also delta knot, here also delta knot, here also delta knot is there. Okay, so why here that gap is somehow looking bigger, here somehow is looking bigger difference, here is looking bigger difference, but everywhere the delta knot is one value. So this is very like what is that values of delta knots. Okay, according to the value of delta knots it will be varied, but that gap is always delta knots. Okay, now another points that why this here that peak should be one transition edge should be we get, and peak should be clear, that one peak we should get. But whenever you look that peak in the spectroscopy, then we see that some soldier's peak is observed. So the reason behind the soldier peak is regions for broad peak. We observe that the regions is that, so whenever you see actually that the peak we should get, that one peak we should get, but that actual peak will be coming something like this. like that peak will get. So why this peak, this type of peak will come? So that region is, see that here what is that, this is there for D1. Okay, so one electrons are there, so you are doing the transitions. Okay, one electron I am doing the transition, so I do the transitions here. Okay, so here what we see that here this is triply degenerates, triply degenerates. So whenever this triply degenerates is there or doubly degenerates is there, then what will comes, that JTD will comes to play. So according to the JTD, what he says that here, this value will be according to JTD, what you see that this one electron is there, and this is, let's say, dx square minus y square, and let's say this is dz square. Okay, and this is dxy, dyz, and dzx. Then what happened, that this will be treated in this, if JTD comes to play, so this will be come to like this. This will become, let's say, dz square, let's say this is dx square minus dy square, and where the electrons is there, so dz square. This is d xz, this is dyz, and another will be where electron is there, that is dxy. So electrons will be here. So from here, that electron transitions possibility three cases, either it will go to from here to here, it can go, or here it can go here, or it also go to here. So three transitions it can do. Either it can go from here to here, these electrons can go from here to here, also it can come to here, or it can also come to here. So three transitions are possible, and we see that every cases there's difference from here to here, difference, and from here to here, the difference is difference from here to here. So here the both the cases, here the difference is different. So the difference between this to this is, and this to this, and this to this is different. So due to this difference in the energies of the transitions, so the peak observed is also different. So that's why the peak will be observed somehow, that which is the bigger. So for that, if that high delta knots, if high delta knots, then that will be that this type of values we can look that for that, here that high is there, so for that this will be the, that's why this broad peak will be observed, peak observed. Okay, so this is the one regions, and other regions also we can explain by, this is region 1, we can say. Another region also we can say that we see that here D2. Okay, so we have discussed in that terms, what we say that here, that this is that L 2s plus 1, this is that terms. Okay, so here that 2s plus 1, this is equal to 2, so here s is that is 1 upon 2, that is 1, this is 1 upon 2, and L is D means 0 1 2 3, so this is S, this is P, this is D, so L is equal to 2. So here if I calculate the J values, that is LS coupling, then how to get the J, that is L plus S dot 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 L minus S. Okay, so this L is 2 plus half 2 minus half. So this value will get that this is 2 upon 2, that is 2 upon 2 1, so 1, so this is going to become 4 4 1 is 5 upon 2. Okay, and this is, if I do that, this is half. So what are the values are there? 5 upon 2, then we will get 3 upon 2, then we will get 1 upon 2. Okay, 5 upon 2 minus 2, then that is 3 upon 2, and 3 upon 2 2, then 1 upon 2. Okay, so these are the j values. Okay, so these j values are there. So now how it is actually looks. So for d2, the possibles are the for this is a d2 5 upon 2, and d2 3 upon 2, and d2 1 upon 2. So these all are the tensions possible. So if you do that Orgel diagrams, so what actually if the Orgel diagrams will comes. So let's say that is uh, what is saying that whenever d2 is there, so for that what are there, t2g plus eg's are there. So for one d2, that I will draw like this. Okay, and another I can draw or I can draw here, that is or sorry, that is wrong. Okay, 2 upon 2 minus 1 upon 2, the value is 4 upon 2 minus 1 upon 2, that is going to be that 3 upon 2. Oh sorry, sorry, this value is 3 upon 2, 3 upon 2. Okay, so this is 1 upon 2 is not there, 3 upon 2. Okay, j value is 3 upon 2. So what are that there only this is not there. Okay, so if I draw this Orgel diagrams. Okay, so what are the there? So for one this d2, that this are possible, this is the Malkin notation. So for one I will draw here, let's say. Okay, this is for d2 5 upon up to. So for this, if for d, that are the t2g plus eg. So these are the that it means that 2 t2g, because here we see that where that we can draw from here that yes. So this is eg. How will you say which is eg and t2g? So here you see that t2g value is minus 0.4 delta naught, means t2g value is down. Okay, this is the t2g value. Okay, and eg value is 0.6. So this 0.6 value is for this non-degenerate state. Okay, so if I write t2g, and this is for that non which is the degenerate state, this t2g value represent for the degenerate state, that is here for triply degenerate states, and for here that 0.6, this value represent that degenerate state, that here is eg. So this is actually eg value, and this is actually t2g value. Okay, so assign the values of Malkin notations to that orbitals diagram which is degenerate state is there. So this value I assign to this value, this then this degenerate states. So that is 0 minus 0.4 to T2G. Okay, and this 0.6 to EG. So this value is T2G value is less, so here I will do T2G, and this value is minus 0.4 delta knots, and EG values I see that that is 0.6 delta knots. Okay, so assign that degenerate states to that, assign these values, these CPSC values to the degenerate states. Okay, so this is the this value. This is for D pipe 2. Similarly, another is the D3 upon 2. Okay, so this I will do here, then I will do here like this. Okay, so for this, these values are also the same value. This is EG and this is T2G, and its value is, let's say, 0.6 delta knots, and this is minus 0.4 delta knots. Okay, so now that what happened, that whenever you do the electronic transitions, then transitions are possible. This is the ground state. So from here the transitions can possible to here, transitions can possible to here, transitions are can possible to here. So three transitions are possible. Okay, and what we see that this energy gap are, if you look, actually draw, if you look spectroscopy, these energy gaps are very less, this and this and this. So due to this energy gap is very less, so that's why this broad peak will occur. Okay, so one, that is due to less energy gap, a broad peak will occur. Peak will occur. Okay, because this energy gaps, this are very less. Actually, I'm drawing like this, but if you look that spectroscopic, that then these gaps are very less. So due to this, that the transitions are, these electrons can go here, go here, so this comes down here. So this type of electrons are occurring, that is in a very speed, very fast. So for that reason, a broad peak will occur, means electron is moving here and here and here in a very fast manner, because the gaps are very less. These gaps and these gaps are very less, very comparable. Okay, so that's why that broad peak will occur. So this is the second regions, and third regions also we can say that, we can say that here that ml bond, we can explain likewise. Let's say ml is there, one time it is stretching is occurring, and let's say this is that ml bonds, and other times compressions. So stretching and compressions, when it will stretch, then what happened that due to ml and bond will be whenever they are stretched, then that delta knot value will be decreases. So if metal and ligands are far away, means that delta knot value will be less. If delta knot value will be less, then, or we can say that when this ml and m and metal and ligands are stretched each other, they will go far away. If they will go far away, then means repulsions will be decreases. So if repulsion is decreases, then delta knot will be decreases. And for that compressions, compression means this metal and ligands are coming each other's, they are coming to the closures. If they come through the closures, then the repulsions will be increases, and if repulsion is increases, then delta knot value will be increases. So, and this is happening in a very fast, like from here to here, this is stretching and compressing, stretching and compressing, so very fast. So delta knot increasing, decreasing, increasing, decreasing. So due to that also broad peak will be occur. Okay, so due to fast happening of both repulsions, both stretching and compressing between metal and ligands continuously, the broad peak occur. Okay, so these are the reasons why we get that some we will not get the single peak, but we will observe in the spectroscopic signals a broad peak will be observed. Okay, so we discuss about of that D1 for our Orgel diagrams for D1. So we will discuss in a simple manner that Orgel diagrams which happening from this T2G to EG. This is EG, and this T2G to EG, the Orgel diagram is happening, and we get that one transitions. But actually, it will be the broad peak we will get. But we will talk about how the transition is happening from here. We will say that from T2G to EG. Okay, from this T2G to EG. Okay, one electron transition is happening. So I will discuss more so that we will get clear. So next will be, let's say we will discuss on D1. Okay, now we will discuss about of D9. Okay, or we can discuss the type 1 are D1 and D9 and D4 and D6. Okay, so let's discuss about of D9 because we already discussed D1. Okay, for D9, if I draw that Orgel diagrams, for D9, if I draw the Orgel diagrams, then let's say 1, 2, 3, only high spins are allowed. D1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, so for this, how many holes are there and how many, so whether we do hole transitions or electron transitions. Okay, past question is hole transition or electron transitions. So electrons and hole. So how many holes are there? One hole. Okay, how many electrons are there? So this also I can do here, this also I can do here, this also I can do here. Okay, so holes are 1 and sorry, electrons are 1, 2, 3. So 3 I can do the transitions. Electrons are 3 transitions according to the electron transitions. If I do the whole transition, then only one hole is there. Okay, so either I can do this one, or either you can do this one, either you can do this one. So only one transitions, one hole can be transferred from here to here. One hole can transfer, but for electrons, this can I can do, this can I can do, this can I can do. So for according to electron, 3 transitions. According to hole, 1 transitions is possible. So I will do hole transitions, not electron transitions. Okay, so if I give that sheet, then what I do, sorry, so I will do the transition, then I will do the hole transition. See here hole is there, this hole will, I will do the transition, this hole will comes to here. Okay, I am doing the transitions of hole transition. Let's say that 1, 2, 3, okay, 4, 5, 6. So this one I will do 6, 7. So this one I will do the transitions to here, I will to here. Okay, so if I do transition, then that will go to, this is already electrons is there, this one I will do the transition, so that will be goes to here. So here hole is come. Okay, now hole is comes here. So previously holes was here, so hole transitions happen from here to here. Okay, this is the hole transitions. So this is T2G, so sorry, this T2G and EG assigned to that where that degenerate state is there. Okay, so degenerate state here, no degenerate state is there. Degenerate state was where it was present, degenerate state was present here. So this I will assign EG. Okay, I will not assign here, I will assign that EG and T2G where the degenerate states are there. Okay, you can write, assign that EG or T2G where degenerate states are present. It is present. Okay, so here that degenerate state is present, so I will assign here. In this case here degenerate state is present, so I will assign here T2G. Okay, because this is triply degenerates, that's why T2G. Here this is doubly degenerates, that's why I asked here EG. Okay, so all transition is happened from EG to T2G. So here to here, all has transition. So I will do that, right? Transitions happen where from EG to T2G. Okay, from EG to T2G happen. And one more thing, that now I will write that spectroscopic terms. So we know that D9, this is D1 or D9, that is D2, and this D2 has that molecule notations is T2G and EG. Okay, so this is 2, so I will write here also 2 and 2. So here also comes 2 and 2. So this is that electronic transitions. Okay. Now calculate the CFS value. CFSE. So CFSE value is, what is the CFS value of this? Then so this is cancel with each other. So see that this. So you know that the very past calculations how you do. Let's say if whenever this is there. Okay, so whenever this type is there, 1, 2, 3, 4 and 5, for this case CFSE is always 0. Okay, so if more than one electrons is gone and this type of transfer CFSE is 0. Okay, now also whenever it is like this, here also CFSE is 0. Okay, so for that, for both case CFSE is 0. Okay, now here that this is, so I will first consider in this if I take this case, then CFSE is 0. So after that, what are that? This is 1, 2, 3. Okay, because this one I take as 0. So above also 2 is there, below also 2 is there. So I have take CFSE 0. So after that, what are remaining? 1, 2, 3 and 4. Okay, so now for this I will say that for this is 0.6 and this is minus 0.4. So how many are there? 1, 2, 3. So 3 means that will be minus 1.2. Okay, and above how many is there? Only 1. So plus 0.6. So total will be minus 0.6 delta naught. This is the CFSE. Similarly here, so first I will cancel with each others. So if this term, then CFS is 0. After that, what are the remaining? This is 1, 2. Okay, so this is minus 0.4 and this is 0.6. So this will be 1, 2. So that will be minus 0.8 and here 2 is there. So that is 1.2. So that will be 0.4. Okay, so for this T2G values, we know that how to calculate the CFSE value. So this value I will get 0.4 delta naught. Okay, this is 12 and this is 8. This is minus 8, this is 12. So that is 0.4 delta naught. And this 0.4 delta naught is for this where that T2G where I assume where non-degenerate state is there. So this is the T2G. So this is value for T2G. Okay, and this is that EG. Okay, so this CFS value is for this EG. This is minus 0.6 delta naught. Okay, so now I will draw that Orgel diagrams. So here that energy, here ligand field strength. So this is that what is that D, that is T2G and EG, and this is D2. I will write here D2 and these are T2G and EG. I will draw here T2G and EG. And which CPS is less, we look from here that this is that minus 0.6 delta knots, and this value is 0.4 net loss. So Eg value is less here. Okay, this Eg value is minus 0.6 delta knots, so Eg will come here, and this value is 0.6 delta knots, and here that T2G value and its value is 0.4 delta knots. Okay, so this is the values, and now the transitions is happened from here to here. Okay, so this transitions is that is Eg to T2G. Okay, this is the transitions, and this is the whole transitions, which is that is whole edge transitions. Okay, so similarly this is for D9. Okay, similarly we can go for D4. So I will fill the electrodes. This is 1, 2, 3. Okay, so I will always fill that high spin. D4 low spin is not allowed, only high spin for Orgel diagrams. Okay, so 1, 2, 3 and 4. Okay, now I will do that Orgel diagrams. Okay, and now so here we see that what are the possibles, whether hole I will do the transitions or electrons I will do the transitions. So here we see that here it is hole transitions. For according to hole, how many, that one transition is possible, and according to electrons, how many transitions are possible. This also I can do, this also I can do, this also I can do. So according to electron, 3 transitions are possible. So I will talk here according to that hole transitions. Okay, for D9 case I talked according to that okay, D9 case also I talk about according to that hole transitions. Okay, for D4 case also we will talk according to the hole transition, because if I talk about electron transitions, then 3 transitions are possible, but according to the hole only 1 transition is possible. So I will talk about this, I will not talk about it. Okay, because we need that minimum transitions. So if I do here, then this, sorry, so this and this, and I can do that this transition. So one hole is transformed from this to this. Okay, so we will assign that these values. So here we see that we assign that where degenerate state is there. So this is the degenerate state here, so I will assign this value. So this value is, so this is W degenerate, so I will do that EG. Okay, and this is triple E degenerate, so I will write here T2G. I will not assign this because this is here degenerate state is, this is not degenerate state. So for non degenerate state I will not assign, I will assign only for the degenerate state. So I will assign over here. Okay, so now this whole transition is happened from EG to T2G, and this is for D4. Okay, so whenever you are talking about of D4, then we see that D1 and D9, that is D2 and D8, that is DFF3. Okay, and D3 and D7, this 4, and whenever I talk about of D4 and D6, I will talk about of this D5. Okay, so I will talk now, I will talk about of D4. D4 means D5. Okay, so here the transition is happening from EG to T2G. Okay, so this is EG to T2G. Okay, and this is that the spectroscopic terms or terms is what, that is D5. Okay, so D5 also has that T2G and EG is there. So if it is D5, then this is also 5 and 5. So it means here also 5 will come, here also 5 will come. So this is the transitions. Okay. So now calculate the CFS value. So if I calculate the CFSC value, then this will be for this case how much value will get, that is this is 0 point minus 0.4, so that is minus 1.2, and this is plus 6, that is going to be minus 0.6 delta naught. Okay, for this case if I calculate CFSC, then and this value is how much I will get, minus 0.8, and this is 1.2 delta knots. Okay, so if I do it, then it's going to be 0.4 delta knots. Okay, so what we see here that this case, so whenever, and this is that low energy, and this value is assigned to non-degenerate state, so this CFS value is minus 0.6 delta knots, and this values, this T2G value will be assigned from here, that is 0.4 delta knots. Okay, now we will draw the Orgel diagrams. So this is energy, and this is ligand field strength. Okay, so now if I do that Orgel diagrams here, then this is D5, so this will be like this. Okay, and we will look here which energy, Eg energy is 0.6 delta naught, and this is 0.6 delta naught minus 0.6 delta knots. Okay, and this value is 0.4 delta knots. Okay, so Ag value is minus 0.6 delta knots, means low value, so Eg will come here, and its value is minus 0.6 delta knots, and this value is 0.4 delta knots, that is value is T2G value. So electron transitions which happen from here to here. Okay, this value is delta knots. So here transitions happen from T2G to Eg. So this is the Orgel diagrams. Orgel diagrams. Okay, so similarly I draw for octahedrals. Similarly we can go for, this is for D4, and previously D1 and D9 we discussed. Okay, similarly for, we can go for D6, because D6 also lies in these types. Okay, so D6, I'm talking about a octahedral only. Okay, so now, so here also we can do that. 2, 3. So I will put 1, 2, 3, 4, 5, and 6. If I do that electron transitions, then what I'll do, okay, so here what are the possible, so if I do the hole transitions, then hole are present here, also hole is present, this can I do the hole transition, here also hole transition possible, here also hole transition is possible, means that how many possible are there, here also I can do the transitions, so 2 holes are there, but electrons only this one is, this one only I can transfer, this one I can't do, because if I do, then that spin will change. Okay, so hole transitions how many are possible, 2, and electron transitions how many are possible, 1. So I will talk about electron, not hole transitions. Okay, for this case I will talk about electron transitions. So from here if I do to here, then I will do this, I will do the transitions here, so this, then this is there. Okay, so I will assign the value only to the degenerate states. So here degenerate state is not there, here degenerate state is there, so I will assign T2G. Here degenerate state is not there, here degenerate state there, I will assign here Eg, or we can write Eg. Okay, T2G. Okay, now CFS value I will calculate and assign this CFS value to this value. Okay, so CFS will be here, how much, so all are filled, so that will be 0, and this is minus 0.4 delta knots. Okay, so in this case whole hour field only here is there, so that is 0.6 delta knots. Okay, this is the CFSE. So this value I will assign to this value. Okay, 0.6 delta knots, and this value is minus 0.4 delta knots. So if I do that Orgel diagrams, so here that energy, and here is ligand field strength. So I will do here. Okay, so which value is less, that is T2G value is less, so T2G, this is minus 0. Delta knot, and this is 0.6 delta knot. So T2G value is here, so I will write here T2G, and that value is minus 0.4 delta knots, and here EG, and its values comes to be 0.6 delta knots. Okay, 0.6 delta knots. Okay, so that electron transitions is from here to here. Okay, so where that electron transitions happen here, from here to from T2G to EG. Okay, so electron transitions is from T2G to EG, and this is for D6, and D6 is, let's say that that D1 and D9, D2 and D8, D3 and D7 and D4 and D6. This is D2, D3, 4, and this is 5. So this is D5. So D5 has EG and T2G. Okay, so why I am doing these things? So I've already told that this. So this is this value. D has these things, and its values are from here. This is the D. Okay, D has D4 and D6 have D, and if D is there, D value is T2G at EG, and if it is D5, then this is also assigned to here 5 5. Okay, if it is D2, then D2, then here also we will assign that 2 2. Okay, same things I am doing here. Here it is D4 and D6 also 5, so I will assign also here 5 5. Okay, here also I am assigning 5 5. So this is the transitions. Okay, so electron transitions are from here to here, and we assign this value. So this is the Orgel diagrams for D6. So I have discussed for octahedral. Similarly, we go for tetrahedral cases. Tetrahedral cases also we can go. So if I go for first, I will go for T1, and that is for tetrahedral. So I will do what, the same things, but here this will comes here, it will become like this. Okay, so D1, so 1 electrons. Now I will do the transitions here. Okay, this transitions, so here electrons and hole transitions. So electron transitions are 1 and hole transitions are 3. So I will do for electron transition, not hole transitions. Okay, so here this will goes to here. Okay, so I will assign this T2G or EG to the non-degenerate state. So here the degenerate state is there. So here that will be, this is, since this is the doubly degenerate, I will assign here TG. I will not assign here because here non-degenerate state is there, because it is non-degenerate state. Okay, now I will assign not here, I will assign here, that is T2G, because this is triply degenerates. Okay, because this is doubly degenerates, 2 orbitals there, that will EG, because E means doubly degenerates and T means triply degenerates and A means non-degenerates. Okay, so here we are not talking about of A, because that we will discuss later, but non-degenerate state we will not talk. Okay, so A will assign to non-degenerate states. but here there are no rules of non-degenerate state, so we will not talk about of A. Okay, so I am talking only triply and doubly degenerate. Since there are two orbitals are there, so that is doubly degenerate, that's why I assign AG. Here this is triply degenerate, so that's why I assign T2G. Okay, and I will assign this EG and T2G only which are degenerate states. I will not assign this value to the non-degenerate states. Okay, so now EG and T2G. So now we will calculate the CFSE value similarly way. So if I calculate the CFSE, so now you see that here the two orbitals are there, so I will do that 0.6 minus, and here I will do that 0.4, because 4 into 3 that is 12 and 6 that 2 that 12, so both should I get 12 and 12. Okay, so I will multiply by 0.6. so how many electrons are the one, so this CPSE will be going to get minus 0.6 delta naught. Okay, similarly for here, how many are there here that above, so here that is 0.4, so here I will get one electron is there, so CFSE is going to be 0.4 delta naught. Okay, so these are the things. So I will assign this CFSE value to this is value is 0.4 delta naught, and this value is minus 0.6 delta naught. Okay, so now I will do that. Now I will do that Orgel diagrams. So this value is less, so Ag will comes down, and note that for this tetrahedral case, this Eg and T2G will not come, because here that COS is not present. Okay, cos is not present, so here we will not talk about of Eg and T2, Eg T2G, not like, you simply say E and you simply say T2. Okay, that is the difference between octahedral and tetrahedral, and that in case of tetrahedral this triple degenerates comes above and double degenerates comes down. That is the only difference between tetrahedral and octahedral. Okay, so this is that LFS, ligand field strength, and this is the energy. Okay, so now I will do. Okay, so which value is less? From CFS we can say that this is minus 0.6, and this is for E, so we will write E, and its value is minus 0.6 delta naught, and this is T2, and its value is 0.4. So electrons are open from this to this. Okay, and that electron transition is happening from this to this, that is from E2, that is happening to T2. And what is that D1 tetrahedral? So tetrahedral or octahedral, this is always same way, this is comes to be D2. So if D2, then this is T and E, so 2, then here will also 2 and 2. Okay, so I will do here 2, here also 2. So this is the electronic transitions from E2 to T2. Okay, E2 to T2. Okay, so this is the Orgel diagrams. Similarly, where you can go for same case for D9 tetrahedral. Okay, so for that also you can do that same way. Okay, so we can feel that, and this is always high spins, so I can do 1 2 3 4 5 6 7 8 and 9. Okay, so I will do that one electron transitions here. So here that I will talk about of electrons, and I will talk about of hole. Okay, so which I will talk. So here that 2 electrons are possible, but a hole are only one hole is possible. So hole is 1, electrons are 2. So I will not talk about electron, I will talk about a hole. Okay, So here we will see that 1 2 1. So this is possible. So I will assign that CFS value to the non-degenerate states. So here this is the degenerate state is there. So this value is T2 and its value is comes to be how much? This is, so this is 0.4. So this value is going to be 0.4 delta knots. Okay, and here it is that degenerate state is here. So here I will do, and its value is going to be 0. So the CFSC will be minus 0.6 delta knots. Okay, so or maybe that will cancel it with each other. So this will be how many? 2. This will how much? 2. That is going to be 0.8 plus this will be minus that is minus 1.2. Okay, so this value is going to be how much? Minus 0.4 delta knots. Okay, sorry. So this value is should be how much? This is 3 are there, and that is 1.2. Okay, plus this is minus 0.6. This is going to be that 0.6 delta knots. Okay, so this value is going to be assigned to this value, that is E, and this is value to T2. So if I do that Orgel diagrams, so that whole transition is happening from where? From here to this happens to here. Okay, so from that is T2 to I will do to E, and this is D9, and D9 case it is going to be D2. So there I will do 2 and 2, and this is the electron hole transitions, and this Orgel diagrams. If I that energy and if I do that ligand field strength, then I will do that here and here, that is D2, and here I will write, so which energy is less? Look from here that this energy is less, so that is T2. So I will write here T2, and its value is minus 0.4 delta knots, and this is E, that is 0.6 delta knots. So electron transitions is happening from here to here. Okay, this is the Orgel diagrams for tetrahedral D9 cases. Okay, similarly you can go for I will do last other things, so you can do the same way. If I do for D for tetrahedral, so for D for tetrahedral you can do the same manner, 1 2 3 1. So I will fill the electrons 1 2 3 and 4, and again so here that electrons are 1 2. So I will talk about electrons and hole. Okay, so if I talk about a hole, then one hole possible, and if I talk about of that electrons, then 2 electrons as possible. So I will talk about a hole, I will not talk about a hole. Okay, so if I do that, then this, so one hole transition is happening from here to here. Okay, so and calculate the CFS and assign these values where non-degenerate state is there. So this is non-degenerate, this is a degenerate state, so I will look here T2, and here I will look for E, and this CFS value will be that we see that here, that is this value is what, 0.6 minus, and this is plus 0.8, that's going to be 0.2 delta knots. Okay, its value is 0.2 delta knots, and its value will be that you can see here, that is CFSC value will be, that is this is 0.4, so that is 1.2, and this is plus 0.6, this is minus 0.6 minus 0.6, so that value is going to be 0.6 delta knots. So this value is lower, just a minute. This is 0.8, and this is minus 1.2, that is going to be minus 0.4 delta knots. Okay, this value is 1 and this is 0.6, that is 1.6 delta knots. Okay, so these are the CFS values, so we can put here, and this is from happening from where, from that is T2 to this is happening to E. Okay, and this is D4. D4 means that is going to be D5, so I will put here 5 and 5. Okay, so these are the electronic transitions. If I do that Orgel diagrams, then this is energy and this is silicon field strength. So I will put here which energy is less. Yes, so that is T2. This is the T2. So T2 value is this. So I send this values to T2. So T2 is, and this is minus 0.4 delta knots, and this is E, and its value is 0.6 delta knots. So transition is from here to here. So these are that Orgel diagrams. So we can draw for similarly D4 I did. Similarly, we can go for D6 tetrahedrals. Okay, so I'm giving that pull the concept in a one page, that whenever the transition is occurring D1, D9, D4 and D6. Okay, for tetrahedral and octahedral cases, what we have to do, that we will do that the Orgel diagrams will be this manner. If you look it, then you will get that do remember that for D1 and D1 and that is for, you see that octahedral case, that is D1 and D4, and tetrahedral case, that is D6 and D9. We have to remember that only one octahedral case, that is on D1 to let me see it. Okay, D1 and D6. Okay, do remember that D1 and D6, I also forgot. So D1 and D6, only you have to remember D1 and D6. Okay, so for D1 and D6, what happened, that Orgel diagram for D1 and D6, this will be like this. Okay, so we will draw this two one like this, another one like this. Okay, and here obviously that here this octahedral, that's why this is always octahedral means how it is. So this is the T2G or EG, whatever that, or T2G, or for tetrahedral, this case octahedral case. Okay, so we will do what, T2G will be here, T2G or T2 also, and here EG or E also. Okay, this one, and here this means here same T2G or T2, here that EG or E. So you can remember by this starting from here. So for D1 and D6 for octahedral, and if you remember this, then tetrahedral force just opposite. So D1, then for opposite of D1 is D9, and opposite of the D6 is D4. So for this the transitions will be always occur like this. Okay, so from T2G to EG for octahedral and tetrahedral. If tetrahedral, then T2 and E, assume that. So transition is always, we will look from here to here only. Okay, so wherever you see that all the transitions wherever you see that for D1 and D6 octahedral and D9 and D4 tetrahedral. So we have discussed for T4 and T tetrahedral, right? We'll discuss about of T4 tetrahedral. Okay, so T4 tetrahedral means from T2 to E. So here you will see that we have drawn that T2 to E. Okay, so wherever the diagram, we no need to draw the diagrams, you just do it and only remember this one. This is very important things, D1 and D6. Okay, not D1 and D4, D1 and D6 octahedral case. This will get, then opposite of D1 is D9, opposite of D6 is D4. Opposite means I am taking D1 and D9, that add should be 10. Okay, so we remember D1 and D6. So D1 opposite is D9, so that 1 and 9 is 10. Okay, so opposite of D1 is D9, and opposite of D6 means I am adding D6 and D4 10, so D6 then another will be D4. Okay, so if octahedral, if you remember D1 and D6, and this Orgel diagram is from here to here, that is same as that whenever you doing that octahedral cases, whenever doing that first T2G and AG. Okay, you will do that, and this will follow for all D1, D6, D9 and D2. For octahedral D1 and D6, for tetrahedral D9 and D4, this will follow. Okay, and the same things here, what will do that D1 and D6, here that tetrahedral will comes, here that tetrahedral case will be this. Okay, D1 and D6, and octahedral will be this D9 and D4. Okay, so this will follows this things. Okay, this will from here to here. Okay, so whenever we see that D1 and D6, always that is EG to EG or E to T2G or T2. So this will be followed. So this we have to remember. We no need to draw that all these diagrams. We have to calculate CPSC, all these things we no need to do. We only remember for octahedral D1 and D6, and that this will follow likewise, and we can do that. And same things here, EG means here EG, here T2G means here T2G. That's it. And with that we solve lot of problems. We no need to draw all this CFSC, all we have to do Hall and electron transitions, all these things not needed. We only remember this much, then that will be the quick answer we can get. Okay, so you remember that this is that Orgel diagrams, and D1 and D6 octahedral, and this will follow like octahedral cases, that is T2 and E. Okay, this is the octahedral. So we will do what? Do like this, cross it up, and this is T2 and E, and this is D1 and D6 octahedral, then tetrahedral will be D9 and D4. Okay, this all follows this type of diagrams. Okay, and if this octahedral, then octahedral we will reverse will done, that is D9, and this is D4. Okay, this opposite of it. Okay, dt will become here octahedral, and tt will become its octahedral, that is D1 and D6. It follows this follows this type of transitions. Okay, that's we have to remember. This is that ligand field strength, and this is the energy. This is the energy. Okay, so only have to remember these diagrams, and we can solve that Orgel diagrams in very quick manner. And we know that how this Orgel diagrams we have to draw it. Okay, so we will discuss the second types in the next class. Second types is type 2, that are D2, D8 and D3 and D7. This type we will hear that 2 electrons or 2 hole transitions are possible, and this we will discuss in next class. So today after this, thank you.